Okay, so we're going to talk through this book here. So after you watch this video, you should read through here and take some notes and study it a little bit closer. But this first chapter here is Science in the Universe, a brief tour. So this is going to be a brief overview of everything we're going to talk about in this course. Starts out talking about the nature of astronomy. We've got the nature of science, how it works, laws of nature, numbers in astronomy. That's some of the numbers we're going to use to describe stuff. Light speed is very fast. Go through a tour of the universe, talk about the universe at a large scale, a small scale, and a conclusion and a beginning. So we've got, in this picture at the top, we've got a couple galaxies here that are actually merging, which is kind of cool and wild to think about. Go down here. So we've got an introduction here. We're going to encounter along our journey here a canyon system so large that on Earth it would stretch across the entire country, and that is this Valles Marineris here on Mars. It's the world's largest, it's the largest canyon in the solar system, thought to be the result of Mars cooling, and as it cooled like a pie crust, it kind of cracked a little as it shrunk. We've got a crater on the Earth, shows us sort of when the dinosaurs, the last generation of dinosaurs went extinct, when we got hit by a big rock, a bunch of other stuff. The moon's gravity is so weak, you could put a baseball into orbit. That's one of Mars's moons. They're actually kind of asteroids. Collapsed stars, so dense you could squeeze every human being on Earth into a single raindrop. That's if every human stood on the surface of it, the gravity would be so strong to collapse all of the humans down into a density that would be the size of a raindrop, which is crazy. Anyway, we've got the Crab Nebula here, which is a picture of a very famous supernova remnant that went off in the year 1054. Bright enough to see during the daytime. There's going to be more of those in our lifetimes, maybe, hopefully. I would love to see that. Not necessarily guaranteed, but we'll talk about that. Okay, so section 1.1 here. Again, you should read all this after I'm done talking to you. But anyway, the nature of astronomy is the study of objects that lie beyond Earth, okay? So that's all it really has to do with. You look up in the sky, what do you see? What's going on? Are there patterns there you can recognize? Try to figure out what's going on. Okay, so throughout this book we emphasize that science is a progress report, right? So we're constantly updating what we know, trying to fit all the facts and pictures together into theories and frameworks and things like that. In 1.2, what's the nature of science? The nature of science, again, this whole idea of the scientific method, it's just a technique to get the answers to the questions that we want to know. You could see a phenomena, you see something happen, and you could think, oh, well, what's the cause of that? And the cause of that, unless you can devise an experiment to predict what could happen based on your explanation really is meaningless. So the most powerful part about science is its predictive ability. So if you want to understand a phenomena, you know you really understand it when you can engineer something using it, and you can make something work and predict how something will work in the future. And so that's the main idea with the scientific method. It's a robust technique. It's a set of steps that you have to take if you want to learn the truth about something. And that's where you observe a phenomena, make a prediction, test your prediction, and if it is verified, then you make another prediction and another prediction until you have a very good idea of how it works. This is these hypotheses that we talk about. If these hypotheses go together and they make a nice framework, and there hasn't been an example of one of your predictions being false, then we eventually promote the idea to something called a theory. Okay, so this just talks through all that, and make sure you are reading this and getting an idea of what science is and how it works, and what it's really useful for. Okay, but let's go on. So 1.3, the laws of nature. So we observe some things that are just the way they are. One of those things is, for example, gravity. When you drop something, you can expect that it will fall towards the Earth. So far, that hasn't been that law hasn't been broken, let's put it that way. So there's other laws, the laws of electrostatics and quantum mechanics and blah, 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 and all these things. These laws, which never break, allow us to predict things in the universe and study things in the universe that we could never hope to go and see. So without the scientific method, all of astronomy is basically useless. So we have to believe that the science we conduct here on Earth is valid across the universe, and that's the main point. Okay, 1.4 is numbers in astronomy. It has to do with things. So we often talk about putting things in powers of 10 notation. 5 times 10 to the 8th, that's 500 million. Okay, so this 8 here is the exponent. So it's basically 5 with 8 zeros after it. So here's that number, 5, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 zeros there. And there's an appendix here you can go to, or here to see different things. The metric system is the system of units we use. It makes it really easy to calculate numbers. But since the distances and times and sizes of everything in space is so just absolutely huge, we have to use powers of 10 notation, because otherwise we would just be having zeros all over the place. Okay, even 500 million is a big number, and that's a human number. We're used to that, $500 million, something like that. Okay, so the common unit that we use in astronomy that you have to get comfortable with is called the light year. And 1 light year is the distance that light travels in a year. So this is an important point. If you flick on a flashlight, the light will go from the end of the flashlight to the wall that you're shining at in a finite amount of time. It is moving at a fixed speed. It's not infinite. So if you imagine sitting at the front end of the flashlight and you turn it on and the flashlight goes off into space, and you imagine how far that light ray would be after 1 year of traveling. That's the distance light travels in 1 year, and that is what a light year is. It's a distance measurement, and because the distances we're trying to deal with are so far, we had to come up with a new unit, and the unit is the light year. Okay, so there's a lot of kilometers in a light year. It's 100 billion, 100 billion, which is crazy. Even the closest star, though, to us is 4 light years away, or 40 trillion kilometers. So that's a really far distance. That's the closest star to us. Our galaxy is 100 or 400,000 light years across. So we're talking huge distances here. This Orion Nebula is a very beautiful picture. It's 1,400 light years away. Okay, that's very far. It's within our own galaxy. Quite beautiful. Okay, so here's a couple examples here. Scientific notation: in 2015, the richest human being on our planet had a net worth of $79.2 billion. Some might say this is an astronomical sum of money. Okay, if we want to express this in scientific notation, so 79.2 billion, it's already in notation, right? So that's its full, how you'd write it out: 100, 1,000, 100 million, 79 billion. But you would write it as 7.92 times 10 to the 10. If you wanted to keep it in billion, it would become 79.2 times 10 to the 9 would be 79 billion, or 7.92 times 10 to the 10. So make sure you understand what I just did there. Another example here, getting familiar with a light year. How many kilometers are there in 1 light year? So light travels 3.3 times 10 to the 5th kilometers in 1 second, right? 186,000 miles a minute. A second. So it's really, really, really far. Let's calculate how far it goes in a year. So this is an example of doing dimensional analysis is the term for it. So if we do 3 times 10 to the 5th kilometers per second, right? We want to know how far it goes in 1 year. So if it goes 3 times 10 to the 5th kilometers every second, and then we can multiply that by some amount of seconds, then that's going to cancel out the seconds and then leave an answer in kilometers. And so that's what we want to do, is figure out how far. So basically what we're going to do is convert, we know there's 525,600 minutes in 1 year, right? If we multiply that by 60 seconds per minute, then we'll get the number of seconds in 1 year. So I'm going to multiply this by 525,600 minutes, and then multiply this by 60 seconds per minute, and you can see that my minutes will cancel out, my seconds will cancel out, and I'll have a huge number at the end of the day. If you work that out, and in this case they started from seconds, hours, and minutes, and so on, and got the total number of days in a year, hours in a day, minutes in an hour, seconds in a minute, blah, blah, blah. And if you multiply them all together, you get this number, and then you get this just huge number, 9.46 times 10 to the 12 kilometers per light year. So that 10 trillion kilometers, that's the distance light covers in a year. To help you imagine how long this is, we'll mention that a string 1 light year long could fit around the circumference of the Earth 236 million times. Okay, well, I don't know if that helps. That's still a huge number. Okay, so anyway, the consequences of this is that the information we see coming from space is arriving minute by minute, second by second, and it came a finite amount of time ago. So if you are on a star or a planet far away and you send a radio signal out to Earth, it's going to travel at the speed of light. And here we are on Earth. Well, there's time elapsing waiting for this light ray to hit us. Bing, there, it just got to us. It took a certain amount of time. So that signal, while that signal is traveling to us, the people over on this planet are doing other stuff. And so then something else happens, they want to send another signal. Well, they got to wait until this signal gets to us, okay? So what this means is that when you look out into space, you're actually looking back in time because you're seeing light as it was when it left. So if I erase all this again and, okay, send a signal. So I'm sending a signal out. Well, and then, this guy has a baby and the signal's still coming to us, and then they grow up and then he dies. Signal's still headed to us, and something happens, they build a new building and this whole planet, and then we get the signal. Well, we didn't know all this other stuff happened. When we got the signal, this guy was still a kid and he didn't have a baby yet, and they didn't build a building and they hadn't died and all this stuff. So if something's 100 light years away, that means it's been 100 years since we last saw it. Okay, the light that just got to us, bing, if this is 100 light years away, if that distance is 100 light years, then the light we get, it took 100 years for that light to reach us, which means we're seeing the light that came to us and it left 100 years ago. If it's 500 light years away, well, that light is 500 years old. If it's 1,000,000 light years away, then that light is 1,000,000 years old. So when we look out into space, the further and further we look out, the further and further we're looking back in time. So there's a word for this. It's called look back time, and it's a way for us to determine the evolution of the universe because we're seeing, when we look out into the distance, we're seeing a younger universe. So that's pretty cool. All right, so 1.6, a tour of the universe. Let's take a brief tour of the universe. So we got Earth. That's our home base. Now there's a hurricane here off the coast of Mexico. So our nearest astronomical neighbor is the moon. We've been there. Here it is to scale. From here to there is the scale of the moon and the size and the distances, which is pretty cool. So you can imagine being a little spaceship that flew over to the moon, orbited, landed a dude on it, 1969, brought him back, and we haven't been back since the 70s. Hopefully we'll be back there soon. That would be cool. I'd like to visit. I don't have to land on it, but just to orbit would be cool. All right, so anyway, it takes about 1.3 seconds for a light ray to travel to the moon, bing, and reflect back. And we have mirrors up there that the Apollo astronauts left behind, so we can shine lasers onto the moon and they reflect right back, and so we can regularly measure the distance to the moon, and we're seeing that the moon is actually moving away from us, which is kind of sad. But okay, so anyway, next thing you got is the sun. It takes 8 minutes for light from the sun to reach us. 8 minutes. Okay, so when you look at the sun during the day, when you feel that warmth, it feels very nice. It's 8 minutes old, okay? So the sun could disappear today. We wouldn't know about it for 8 minutes. 8 minutes is a long time. I've been talking for like 2 minutes. 6 more minutes. That's when light from the sun would reach us when it left, okay? The distance from the Earth to the Sun, this is one astronomical unit. This is a big deal, 1 AU. So this is something you have to just get used to. So if you've got the Sun here and the Earth is orbiting the Sun. The distance from the Sun is defined to be 1 astronomical unit. We use that because we want to compare the other planets to the distances to the Sun. We want to compare other planets in other solar systems to our solar system. So we use the 1 AU as a good reference point. And that's 150 million kilometers. That's how far the Sun is away. Another way to write that distance is not 8 minutes, but 8 light minutes, okay? And 8 light minutes, because it takes 8 minutes for that light to reach us. Bing. All right, it takes, what, 365 days to go around the Sun? Blah, blah, blah. And here's the rest of the solar system. So you got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then you've got the dwarf planets, okay? Ceres is in the asteroid belt between Mars and Jupiter. This is not to scale, by the way, not at all. Pluto is out beyond Neptune. Haumea, Makemake, Eris. There's a bunch of other dwarf planets out there, which is the reason that Pluto is no longer considered a planet, because we discovered all these other guys that were the same size, or bigger even. And so rather than make everyone learn a bunch of new planet names, we just said, okay, Pluto, we're going to demote you, keep the 8 planets here, and then consider these other things dwarf planets. And we'll talk more about that, maybe. Okay, continuing on here. This is not a picture of the Milky Way galaxy, because we do not have a selfie stick large enough to see that. But this is similar to the Milky Way galaxy. Our galaxy is a barred spiral galaxy. Okay, a barred spiral means it's got this, looks like a ballet bar. It's just a very flat bar shape to it, but then it's got this spiral aspect as well. So we call it a barred spiral galaxy. It's got hundreds of billions of stars in it, about 100,000 light years across. In a sphere, this is an important point. Our galaxy, we like to think of it as this like pizza-shaped thing, but it's actually this sphere of stuff. And that sphere is about 100,000 light years across. So it's huge. We're about 30,000 light years from the center of the galaxy. So if that is our galaxy, we're about halfway out from the center. We might have a picture of that. No, we don't. Okay, so we're about 30,000 light years out from the center of the galaxy. Nothing special about it. Here's one star of a bunch of them. If you look through the Milky Way, here it is. There's the Milky Way. This is called interstellar dust. There's a lot of dust there that we see that blocks out some of the stars. On a given night like this, with your naked eye, you could see about 5,000 stars. 5,000 stars out of 100 billion. So even on a dark sky, when it looks like pretty magical, if you've ever seen one, lots of stars everywhere. All of those stars, by the way, hashtag more stars than planets. I'm not going to write that. More stars than planets. Every one of those stars has planets, which means there's more planets than stars. Okay, so that's a kind of wild fact that we're learning about more and more recently, because we're able to detect extrasolar planets. So every star has planets, plural. Okay, this is a cluster of stars. This is a globular cluster. We're going to talk about globular clusters later in the course. Beautiful, right? Just thousands and thousands of stars here. 250,000 stars, really, really close to each other. These globular clusters orbit around the Milky Way. So they orbit up and down and all around. They're some of the oldest things in the universe, actually, these globular clusters. We'll talk more about them later. Okay, so this is really cool. We're made of stardust. We're going to talk a lot about what that means. All right, so the universe on a large scale. Blah, blah, blah. Yeah. Okay, so first thing to mention, we've got a couple of dwarf galaxies. Magellanic Clouds, we call them, the large and small Magellanic Clouds. They are dwarf galaxies that the Milky Way has absorbed. And all of these are eventually going to be in part of our galaxy. There's also the Andromeda Galaxy. Do we have this labeled yet? So the Andromeda Galaxy, there you go. This is the large and small Magellanic Clouds. You could only see these from South America. Not South America, but the southern hemisphere. So yeah, South America, Africa. If you go below the equator, you'll see half of the universe that you don't see up here because the Earth normally blocks it out. The Andromeda Galaxy you can see from the northern hemisphere. This is a picture of the Andromeda Galaxy. Very beautiful galaxy. It's close by, 2.5 million light years away. So it's the closest full-size galaxy to us. It's a galactic neighbor, but it's still 2.5 million light years old. So when we're looking at the closest galaxy to us, it is light from 2.5 million years ago. So they're looking at us. What they see is us 2.5 million years ago. So, you know, there's some woolly mammoths walking around and doing some other stuff, but no TVs, no planes flying around, no life as far as they can tell. So we may be in the same boat trying to look out and discover life in the rest of the universe, and we can't see it because it hasn't evolved yet, because we haven't let the light from the hasn't reached us yet. I want you to take a really important look at all the stars in this picture. Those stars are within our own galaxy. What I want you to notice about them is look at all the different colors. Okay? This is a really important thing about stars that we're going to talk about. They have very varied colors, and what causes them to have different colors, and what does that tell you about the star? So pay attention to that, because we'll talk about that a lot. There are galactic clusters. Every spot of light in this image is a galaxy. So galaxies do get together and they gang up and gravitationally are related with superclusters. So our group of galaxies is called the local group. It's part of a supercluster of galaxies, which is called the Virgo supercluster. And so all these galaxies, hundreds of billions of stars in each one of them are their own little islands, and it's kind of amazing. The whole universe is this network of filaments galactically or gravitationally related to each other. So at even greater distances, we find these things called quasars. So you look really out into the farthest you can see with a telescope, and the galaxies get dimmer and dimmer and harder to see and harder to see. But then there's these things that are super bright that are called quasars, which are short for quasi-stellar radio source. Brilliant centers of galaxies glowing with the light of an extraordinary energetic process. There's black holes, basically, that we think ejecting huge amounts of energy when they consume their immediate neighbors. Okay, so that's pretty wild. So those are just some of the things. We'll talk more about those down the road. All right, the universe is very small. So in empty space, you've got some atoms occasionally. It's very empty, usually. There's some elements that we see when we look out into space. We'll talk about how you can measure them. But hydrogen, helium, carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, iron. You know that these are the building blocks of chemistry and life on Earth, and we find these abundantly all over the galaxy. So it's kind of amazing to see all these. There's amino acids out in space. There's all kinds of really cool stuff to detect. Okay, now there's an important thing here which is a little bit wrong. Okay, remarkably, physicists have discovered that everything that happens in the universe, from the smallest atomic nucleus to the largest superclusters of galaxies, can be explained through the action of only four forces: gravity, electricity and magnetism, and the strong and weak nuclear force. Okay, 4 forces. Okay, not just a million or one, as puzzle physicists astronomers led to a quest for a unified picture of nature. We think that there's probably only one force, or at least we can write down one equation that combines all these forces together and apply them in different ways to get the predictions of everything. We can predict and control and calculate what would happen in basically any circumstance, except that at the center of a black hole. That is still the only spot where our theories break down. And that's really a problem to figuring out everything else. So anyway, we'll talk about all that later. And a conclusion in the beginning. So, just read this. This is cool. Basically, this is the history of the universe, okay? You've got this thing called the Big Bang, which we'll talk about, the beginning of this era of the universe. We don't think it's necessarily the beginning of everything. And then the universe evolves over the course of a year. We're imagining the full 13.7 billion year lifetime of the universe. We're imagining it broken up into 1 year or scaled to 1 year. So from January to October, you basically have nothing as far as Earth is concerned. In October and November, that's when life starts to form. That's when the Earth forms. In about, a couple billion years ago, life starts forming. If you look at the last month of the year, okay, it takes until the last couple weeks before you get plants and weird little creatures, dinosaurs appearing, mammals are appearing, and then dinosaurs become extinct. And in the last hour of the last second, here you go, the invention of the alphabet doesn't occur until the 50th second of 11:59 p.m. on December 31st. So humans, so far, and the amount of stuff we've discovered in the short time that we've been around is kind of remarkable. And it's only really been in the last 100 years that we've figured all this stuff out. We didn't know that other galaxies existed until Edwin Hubble observed Andromeda Galaxy and realized it was outside of our galaxy, and that wasn't until 1922. So that's kind of amazing. So anyway, so that's chapter 1. Make sure you read through that. There are some good questions. Now there's no questions at the end of chapter 1. So that's an introduction for everything that we're going to do. Okay, have a good night.